Wait a moment.
Okay.
Sorry, maybe you can let others to try to share first. There is
Okay.
some problem with my Mac.
Okay. So maybe the second presentation speaker, Oscar, you can test your screen sharing first.
Okay, can you hear me, right?
Yeah,
Okay.
sure.
Okay, yeah, I can start then, no problem. So I will share my screen and okay.
Yeah,
Okay.
yeah, great.
So I am Oscar Cornejo from University of Luxembourg, and I'm going to present our tool MAS for mutation analysis of space cyber physical systems. So this is a work done with Fabrizio Pastore and Lionel Briand. So the motivation for this project lie in the fact that software has a prominent role in space systems. So, and as a consequence, software failures have high impact, ranging from explosion to loss of large amount of data. But how do we ensure thorough testing in space systems? A valid way is mutation analysis, which consists of automatically generating faulty versions of the software under test that are called the mutants. And then we are going to test this mutant against the test suite for the software under test. The mutation analysis metric is the mutation score, which is a percentage of mutants leading to a test failure. Ideally, all the mutants should lead to a test failure, but in practice, we may have mutants that are equivalent with the software under test, and other mutants that are redundant within each other. And all of these affect the pertinence of the mutation score as an adequacy metric. Also, the presence of a large number of mutants introduces scalability issues, especially when the test suite takes hours to execute like in cyber-physical systems. So to account for all these problems, we have developed a pipeline that is called mutation analysis for space software. The first step of this pipeline consists of collecting code coverage information from the test suite. Then we generate the mutants, and for this we rely on a set of operators indicated as effective in the literature, such as the sufficient set, the deletion set, and the LPR operator. Then we compile the mutants. Then we remove those that are considered equivalent and duplicate based on compiler optimizations, which is standard practice. We compile the software with all the available options, and we compute the hash summary for each generated executable. So to detect equivalent, we compare with the original software, and to detect duplicates, we compare pair mutants belonging to the same source file. Then we sample the mutants to execute, because we cannot execute all of them. So for example, let's say the mutation score of a system is 65%. So when we sample, the estimated mutation score will vary based on the number of mutants that we are sampling. With a larger sample, we will obtain a mutation score that is close to the actual one. So we would like to subsampling when we are close enough to the actual mutation score. So for this, we develop a method to determine when we are close enough to the mutation score based on the computation of the confidence interval. So we rely on a fixed width sequential confidence interval FSCI approach, which means that we stop sampling when the range is small enough, in our case, when the range is below 10 percentage points, which means that the mutation score returned to the end user should be at most 5 percentage points away from the actual mutation score. So assuming that the mutation score follows a binomial distribution, we rely on the Clover-Pearce method for CI computation. So basically, this is the loop that we execute. We sample the mutants, we execute test cases, we evaluate the mutation score confidence, and we sample additional mutants if the range is not small enough. And then in step 6, we execute a reduce and prioritize set of test cases. So for test suite prioritization, we rely on state coverage information. And basically, we have a greedy algorithm that selects first the test cases with the largest distance from the closest already selected test case. And for reduction of the test suite, we exclude test cases with a distance of 0. In the step number 8, we discard all likely equivalent mutants by disregarding those live mutants that do not show a difference in code coverage with respect to the original program. and then we compute the final mutation score. So to recap the key feature of MAS, we have integrated the discarding of equivalent and redundant mutant based on compiler optimizations. We generate mutants based on the sufficient set of mutation operators. We sample the mutants with FSCI, and we provide statistical guarantees about the accuracy of the estimated mutation score. We further reduce the test suite execution time by reducing and prioritizing the test cases. And we discard unlikely equivalent mutants based on code coverage. All of this to make a pipeline that is scalable and efficient in the context of space cyber-physical systems. Okay, so before going into the demonstration, I would like to introduce the case study that I will share today. So we will now apply MAS to evaluate a test suite for a data encoding library provided by ESA, one of our partners. The library has been generated from a data model specified with the ASM1 grammar. The test suite has been generated automatically from the same data model. The software under test is about 2,800 lines of code, and the test suite consists of 107 test cases. Okay, so I know that you encourage for a live demonstration, but unfortunately, some of the steps of our pipeline take way more than 5 minutes. But so I will present the demo through a pre-recorded video. So before executing MAS, we will configure it a little bit. Okay, so to do so, we're going to edit massconf.sh, and we're going to define the installation path, the directory of the workspace of MAS, the type of build system of the software under test, the compilation commands, the sampling technique that we're going to use, among other optimizations. So even though you see many configuration lines in here, when freshly installed, MAS already provides many default values, so you don't have to take care of it. So we also provide one launcher for every step of the pipeline. So there is one launcher for generating the mutants, executing them, and so on. And we also provide a one-step launcher that runs all the steps at once. So for the first step, we will execute the prepare suite script, where in addition to collect code coverage, we will also collect the list of tests to be executed. We can see the list of tests plus its timeouts on the following file. So we collect the order in which we should run the test, and also the maximum timeout. We can also see that we collected GCOV coverage files as well for each test. So in the next step, we're going to generate the mutants. So there is a dedicated launcher for that. And basically what we're going to do is to, for every covered statement covered by the test suite, we're going to apply every mutation operator that is available. And for this case study, we will generate about 9,000 mutants. All the mutants will be stored in a specific folder. And of course, the idea is that every of these mutants that is being generated shall be detected by the test suite. Otherwise, it could mean, for instance, that the test suite is lacking of a certain characteristic or a certain test case to be more complete. So this is the folder where all the mutants are being stored. And for instance, if we open this mutant, the 642, it means that the line 642 is being applied the mutation operator ICR, which has replaced the last constant by a 1. So the next step of the pipeline consists of disregarding equivalent and redundant mutants, and also discarding the non-compilable mutants based on the trivial compiler result optimization. So for this, we compile all the mutants with several optimization levels of 0, or 1, or 2, or 5, etc. We store the hashes, and then we filter out equivalent mutants when the hash of the mutant is either identical to the hash of the original program. And then we remove redundant mutants when there are mutants that has the same the identical hashes. So in the next step of the pipeline, we are going to generate a prioritized and reduced test suite. So in this step, we will generate a file containing for each statement a specific set of tests to be executed in a specific order. Why we do this? Because if there is a mutant affecting, for instance, line 103 for a certain source, we don't need to execute the full test suite, only the test cases that cover that statement. So we have an algorithm for reducing the test and also for prioritizing in order how likely is that the test case kill the mutant. And we also have another test suite in case that the user wants to use, in which we are not discarding the test cases. And for instance, as you can see for the same statement 103, we also have test 74, test 4, and test 26. Okay. Then in the next step, we will execute a subset of the mutants. So we let it run the test suite against each tested mutant. And we use the FSCI sampling approach, which means that we estimate the sample size dynamically while we are exercising the mutants. So during this step, we will collect also the code coverage information about the mutant and the mutation traces. So these mutation traces include the mutant statuses, the name of the mutant, the test that has been executed, and whether the mutant has been killed or not. So in general, there will be one line per test case executed. Then we identify likely equivalent mutants. What this means? It means that for every live mutant, we compare the coverage profile with respect to the original program. If we see that there is no change of code coverage profile, we consider mutant likely equivalent, so we remove it from the analysis, so it doesn't affect the mutation score. Then all these mutants that are likely equivalent are stored in this file, and they are not considered from the analysis, as I said before. And then in the last step, we generate the mutation report. What this means, it means that we report the total mutants that were generated, that the mutants that were filtered by optimization, the sampling type, how many mutants we execute. We execute only 700 mutants. We report the mutations, the final mutation score, and we also provide a list of useful mutants that should be analyzed by the engineer. The idea of this list is that it provides mutants that have a different coverage profile from the original program, but they were not detected by the test suite, so it could be a shortcoming. So, and for finalize my presentation, I will show an example of a mutant that was not detected by the test suite. So, for this function, tint is constraint valid. The mutant affected this line in yellow and has replaced a 0 by a -1. And the test suite did not detect this mutant. So by looking at the code of the test suite, that invokes that the tint is constraint valid, we can see that PR code is never checked, okay, and it is actually written in this line. So this is basically a shortcoming because it's lacking of an oracle, and basically to solve this, it will be enough to add a check on this if condition to validate the value of the PR code. So I hope everything was clear, but looking forward for your questions. So thank you very much.
Okay. Thanks, Oscar. It's very nice talk. Okay, so is there any question? if you have questions, please just open your microphone and ask. Okay, so I have one question. Is there any difference of the space software compared with the conventional software?
So,
Is it clear?
sorry, I didn't get
Sorry.
I didn't get your question. So
Okay.
is there any
Sorry,
difference between? Okay. Your question is if there is any difference between space software and normal software? Yes? Is that your question? Okay. We cannot hear you. I think you're probably mute. Hello? I cannot hear you. Probably somebody else can say if you can hear Yejun.
No, we can't. I guess his connection is quite bad. So and that's the reason. So.
Okay, but if the question was if there is any difference between normal software and space software, yes, they are different because, for instance, some of the space software, when they are verified and validated, they are not executed in normal computers. They are usually executed under simulators and certain hardware. They use a specific hardware, so we cannot use the same mutation analysis tool that we have in the literature. We have to provide specific solutions for those environments.
Okay, so did you have designed any mutation operators that specialized for this software?
I'm so sorry, but I cannot understand the question.
Oh, sorry. I just mean, have you designed any new mutation operators that specialized for the space software?
Actually, there is not a study for a specific mutation operator to be used in space, but we decided to use the one that are defined as the most effective, the one that detect more faults in the software.
Okay. Okay, thank you.
Mm-hmm.
Any other questions? Okay, so since the time is used up, so we can move the next presentation. And if you have any other questions, you also can still ask and type your questions via the chat panel on the right-hand side of the web page, right? Okay, so the next presentation is, okay, the first one is Xinyi. Are you ready?
Yes, I'm ready now.
Are you okay now?
Yes, I'm ready. Can you hear me?
Okay. Yeah, sure. You can share your screen.
Okay. Can you see my screen? Wait.
Yeah, sure, but maybe Oscar, you need to. Okay.
Okay.
Thanks.
Okay,
you can start.
So my name is Xinyi Wang. I'm a second-year master student from Nanjing University of Aeronautics and Astronautics. My topic is QSBT search-based testing of quantum programs. This work is conducted with Paulo, Tao, and Shoka. And first, I can show some differences between a classical bit and a qubit. A quantum program works on qubits, different from classical bits. A classical bit is encoded as either 0 or 1. A qubit can be in superposition of 0 or 1 at the same time until observed. Each quantum program requires inputs for computation. We use binary numbers to initialize input values at the beginning. We get the outputs up, which will be either 0 or 1 for each qubit. Each quantum program requires one program specification. We can use a subset of the input values that are valid according to the program specification. Valid output values are produced by valid input values. For one valid input, there can be one or more than one possible valid outputs, but we can only read one of them after each measurement. And for each input, each possible output value has their expected probability of occurrence. However, there exist many challenges in quantum software testing. We propose QSBT, which is an automatic testing tool. We employ a genetic algorithm with Gematopy framework, and we run quantum programs with QASM simulator on Qiskit framework. The goal of search is to generate a test suite with the maximum possible number of failing test cases. About QSBT, first, I can talk about test case generation. First, we use genetic algorithm to generate a number of search variables as a test suite, which is also an individual for this algorithm. Each variable represents one input. The size of the test suite M can be defined by the users. The user can choose the value beta, which is smaller than 1. Then M equals to beta multiplies the number of possible valid inputs. The fitness function is to maximize the number of failing test inputs in one test suite. We defined 2 failure types for quantum programs under testing. The first one is unexpected output failure, which is called UOF in short. According to the program specification, if the output returned by one input is unexpected, which means that the probability should be 0, this kind of failure is UOF. The other failure type is wrong output distribution failure, which is WODF in short. In order to get the distribution, the tool needs to execute a quantum program with one input multiple times. If the output probability distribution significantly deviates from the program specification, it is WODF. The statistical test we use is a goodness of fit test with a Pearson chi-square test. We compile 2 groups, the frequencies of output we observed and the expected distribution of the program specification. If the p-value is smaller than the significance level alpha, it is a wrong output distribution failure. And here is an overview of our tool QSBT. Users need to provide the quantum program file, program specification, input-output information, together with some parameters of QSBT and the genetic algorithm in a configuration file. Then QSBT begins to generate test suites with genetic algorithm using the fitness function the tool defined, the weight of encoding the individual with input, and other parameters users provide by default. We use QASM simulator in Qiskit to execute quantum programs. We run each test case multiple times and collect the results. By these 2 failure types we defined before, the tool can assess the test results. After finishing the whole testing process, we can get the result files. We conducted the experiments with 5 different quantum programs, by default parameters to evaluate QSBT. We created 2 faulty versions for each quantum program. Results show that QSBT can manage to find more than 50% of the failing test cases for most of the faulty quantum programs. Also, it is very clear that the time for search algorithm takes up only a small part of time. And next is about the live demonstration of our tool. First, I will show some information of the configuration file that user need to provide. First, user should provide an init file, including all the information. The program section includes the keys of the root of the quantum program file, the total number of qubits of the quantum programs, IDs of this quantum program, and IDs of qubits used for input and IDs for the output. Especially the quantum program file can be written in Qiskit. In the QSBT configuration section, we have the keys to define the number of test cases in a test suite and the significance level for judging the failure WODF. So combining the input ID number and the beta, we can know that the test suite size for this test is 26. And here is I can show about how to run this tool. We can run our tool in terminal. Here is the welcome screen of QSBT. If we type in 1, we can see the template of our configuration file that the user needs to provide. It includes some description of all the parameters and all the sections. If we type into, we can see a small example which includes all the information. And if we type in 3, it will guide you to enter the root of the configuration file. So I use the sample file that I showed in the slides. So it will begin to run. The whole running process lasts for about 250 seconds. And because the time is a bit long for us presentation, so I just have prepared it before. This is a file that it can generate. This is one possible file because of the probabilities. Every time we run, we will get different results. And here is one example. In this file, we can see the best solution of the best solutions that the genetic algorithm generate. And here is all the information about the test cases of this test suite. And here is the fitness, which is the number of failing test cases in one test suite. And this is the total runtime. And here is the simulation time of running the quantum programs by Qiskit. And the users can also see the log information of this process. Users can see all the test suites, include the test input and the test results. Also, we can see the number of the failing test cases of all these runs. Also, user can get a file of the unit test for the test suite or this best solution, and it is generated by QSBT automatically. We can run each of them to analyze the outputs. We can see the output of each test. So users can analyze their information in this file to analyze the inputs and get the results. So if you want to download our tool, you can use this QR code. Thank you.
Okay, thanks. It's a very nice talk and very interesting work. So, is there any question? Okay. So I have one question.
Okay.
That because I'm not very familiar with the Quantum program, so maybe the question is very easy or straightforward for you. So, did you have tried other method in software testing in the application scenario of the Quantum program?
Also, you mean that did I use other methods to try this software quantum software testing to analyze different efficiencies of the methods?
Yeah, yeah, sure.
As begin, our baseline is we run random to we use random testing to get the results, and we can clearly see that our result with QSBT is much better than random. And also we have tried some other methods, something like the combinatorial testing to test the quantum programs. But I think different methods can have different scenarios to test these quantum programs.
Okay.
Yeah.
So I have just noticed that you have mentioned the existing approaches may be not very applicable for your application because it's difficult to estimate the quantum program state, right?
Yes.
So how did you overcome this problem?
So for each test input, we need to run multiple times to get the distribution. And we use this distribution to see whether the outputs are correct or it deviates from our expected distribution. And we use this to analyze whether it is correct.
Okay, so you measure the distribution of the expected and the exact. Okay, so in this process, you just set a threshold to measure whether the produced result is correct or not, right? So how do you decide the threshold?
Sorry,
Sorry, so you just compare the running result with the expected distribution, right?
You say the random results and the expected distribution?
Yes. So you will compare the difference between them and decide whether the result is correct or not.
Because for each program, we need to provide a program specification to see because each input has a different expected distribution of the outputs. So I need to run a lot of times to see the distribution if it is similar to the expected distribution. So
yeah, sure. So I just curious about that. You don't you just the test case pass when the result is exactly the same with the expected one, or same expected distribution.
Similar. We
Okay,
use
so how do you measure the similarity?
I can show with my slides about it. Maybe we can see it with one example to, which will be clear. Oh no, there is no example. We use this. We use a test. We use this data statistical way to, and we set the p-value for this. Or we use one significance level to judge our results for this distribution.
Okay, so you mean you use the p-value to decide whether the produced result is significantly different from the distribution of the expected one, right?
Yes.
Okay, thank you. Okay, so any other question? Okay, thanks again for your nice presentation. So let's move to the next presentation. The next one will be test night. The speaker will be George, right? The next one. Okay, the speaker is George Romeo.
Yeah, hi.
Okay, you can start.
I'll start back my screen. All right.
Okay.
Let's see. Okay, so hello everyone. I am Jorge Romeo, and also in the chat are my co-authors, Christian Botocan, Pius Mook, Pablos Macridis, and Madan Razan. We're all bachelor students from TU Delft, and we're here to present Test Night, an interactive testing assistant for IntelliJ. So in this presentation, I'll quickly go over the problem that Test Night addresses, the features it implements, and then a quick demo to show them in action. And lastly, some links in the Q&A session. So if you've already seen the video beforehand, you know that Test Night is a plugin for IntelliJ IDEA designed to help with writing JUnit test cases, specifically for Java. Test Night aims to help with what we call the 3 dimensions of testing, which are first finding what to test or which test cases need to be realized. Then, of course, physically implementing the tests. And then lastly, evaluating your existing test suite to know if you're done or if you need to add some more to cover more branches or more lines. And then the features we provide for each of these categories are for finding what to test. We provide a checklist generation, which will generate a testing checklist for classes or methods, which will let the tester know which test cases need to be implemented in order to fully cover this method or class. Additionally, Test Night can generate some assertion suggestions for a method call, which let the tester know which side effects or post conditions need to be tested for after the method call. Then for the act of actually writing the tests, Test Night allows you to quickly duplicate an existing test and then modify some of the fields, which is faster than the tedious highlighting, copying, and pasting that we're all familiar with. And it also provides the user with some UI to navigate the test suite and generate some of the boilerplate associated with unit tests. And then lastly, for evaluating the test suite, TestNet gives you some additional coverage information on top of the standard coverage information, specifically how your coverage changes over time rather than just the fixed coverage right now, as well as giving you the ability of seeing which lines of code are covered by a given test case. But really, what's the point in explaining the features when we can just do it in a demo? So we can move on to that now. All right, so here I've set up a very simple class that we can write some test cases for. It's just a simple point class, which represents a point in 2D. And the method that we'll be testing is this one here, which takes a given point and then says on which quadrant of the 2D plane it's on. So it can be first, second, third, or fourth. Now, in order to test it with TestNet, what we would first do is generate a checklist, like so. And this will give us a list of test cases that need to be implemented in order to fully cover it. As you can see, it's actually a lot of test cases. And the reason why it's so many is because the criteria it uses for generating these is MCDC coverage. But if we want something a bit more concise, because maybe that's a bit extreme for just a 10-minute demo, we can change this to branch coverage in the settings, where we also have some other settings, which we'll go into later. And if we regenerate the checklist, now we can see it's a bit more manageable. Then for each of the checklist items, we can see which location in the code it corresponds to, so we can kind of easily see what thing we're trying to test. Now, as for actually implementing them, we can right-click and generate the boilerplate for the method, so we don't need to write all of the initial things ourselves. And then we can just give it a name, so test. So I'll put this picture here just for reference, it's useful. So here we want to test for a point being in the first quadrant. So we first need to actually make the point. And then assert that no exception is thrown. Then we'll get the quadrant. And now, in order to know what to assert, obviously in this case, we just need to check the output of this function. But TestNet will allow us to generate assertion suggestions, which will investigate, which will see all of the side effects of the function, and then tell us which post conditions to assert. Now, in this case, the function has no side effects besides returning a value. So that's the only suggestion that we get. So we can now just assert equals to 1 to the quadrant. All right, great. So we have our first test case. But now, instead of having to repeat this process over and over, we can make use of the test duplication item feature. So pressing Control-Shift-D will duplicate the test case, and it will allow us to tab through some of the fields in order to quickly change the values. So we can rename the name. That's the most obvious thing to do. Like second quadrant, and then just change the coordinates, maybe -1 and 1, and the second quadrant, and we can do the same for the other two. All right, so now we have 4 test cases. And what we can do now is run with coverage in order to see how well the tests are performing, if we are thoroughly covering the function. So I'll just give it some time to run. And yeah, so as you can see, we have the standard IntelliJ coverage, green for the covered lines and red for the uncovered lines. But you might notice that the green here is much brighter than what you're used to seeing. And that's because on top of telling you what's covered and uncovered, TestNet lets you know of what has been covered in this most recent test run. So this brighter green indicates that these lines of code in this chunk here and this one here are covered, but are specifically covered by this most recent test run here. So to maybe show this a bit better, we still have one uncovered line over here, this last branch. So we can make a test case for that. Once again, duplicating. And this case corresponds to being on the boundary, so 0, 0, for example. And in this case, we also need to make sure that we do throw an exception. All right, and now if we run this test case as well with coverage, then here we can clearly see that, okay, these lines over here that for this chunk are covered, but they're covered by the most previous run. And then this one over here is covered by this most recent test case run. So then it's useful for the tester to be able to see specifically the impact that this most recent test case has on the test suite. But that's it for the general demo. Besides that, just some other things, I guess, worth mentioning. On top of the standard coverage information that IntelliJ provides, we also let you know of the numerical increase in percentage. So this one last test case gave us an extra 7% coverage. So that might be useful to know. And then, of course, testnet can be collapsed like any other IntelliJ panel. And then besides that, we also have an extensive settings menu, so the user can configure it to suit their needs. You can disable features you don't care about, or change the way checklists are generated, and so on and so forth, since obviously a tool like this highly depends on the user for how you want to use it. But I can go back to the presentation. Yeah, that's it for the demo. Testnet does have some other features that we didn't go in depth because of time limitations, but you can check out the GitHub README, and there's some nice animated GIFs for each of the features, so you can see them in action and see how they work. But yeah, that's it for us. Here we have QR code to the GitHub repo and also to the marketplace if you want to install the plugin and try it out on your favorite Java project. But besides that, if you have any questions, then we will stick around the chat for a bit to answer them.
Okay, thank you. It's very interesting work, and I think it's very useful tool for developers. Okay. So, any questions?
I actually have a question. A very nice tool, but I'm wondering, are there any limitations? So how's your tool handling more complex data types, more complex conditions, or conditions that maybe use library functions? Maybe you can elaborate a little bit on that.
Yeah, I can elaborate on that. So for which feature do you mean? Like for the checklist generation, for example? Or for something else? Yes, so the way it works is that for conditions and like language features like for loops and while loops, there's certain rules that will generate the checklist according to it. But then, yeah, it's much more tricky when you're dealing with a user-created class. So what we can do there is in the settings, you can configure the behavior of how the suggestions will work for each data type. So by default, we include many of the standard data types over here, so arrays and library types and so on. But if you want to change the suggestions for a custom type, you could theoretically add this to the settings. We don't really have a nice way to make this be kind of as a library or as an extension, but maybe in the future this can be added. Yeah.
Thank you.
Okay. Any other question? Okay, so let's thanks again, George. It's a very nice talk. Thanks.
Thank you.
Okay. The last one is the title is Fuzztastic. Okay. And
Yes, let me just
okay.
stop this
Okay.
screen.
speaker is Stefan, right? Okay.
All right, so you can see my screen?
Yeah, sure. Okay, can you start?
Okay, so welcome from my
sorry.
side.
Sorry, Stefan. The third screen is very small.
Okay, then I leave it like that. Can you see it?
Yeah, sure.
Yeah. Okay, so hello from my side. My name is Stefan Lipp. I will present the FASTASTIC tool, which is a fine-grained fuzzer-agnostic coverage analyzer. This is joint work with my colleagues from TUM, as well as with Dr. Marcel Böhme, who leads the software security research group at the Max Planck Institute. So let me first start with a brief motivation why we developed this tool. So there are actually tons of different fuzzers out there, and fuzzers automatically test your program for security bugs. And these different fuzzers come in different shapes, different techniques. And obviously people want to know which fuzzer is better than the other, or is there even one fuzzer that outperforms all? And so, yeah, we want to evaluate that. And the common metric to evaluate fuzzers, the effectiveness of fuzzers, is to use code coverage. However, in fuzzing, capturing code coverage is not that easy because you generate tons or even millions of test inputs. And what current evaluations are doing is that they capture the test inputs that are stored in the fuzzer queue, which is basically a directory that holds only the inputs that increase code coverage. And then in a second step, they replay these inputs on a second instance of the same program, but on that program, you enable coverage support. And this approach has a couple of limitations. So first of all, most fuzzers hash the coverage information, and then you are prone to path collisions, which basically means that coverage increasing inputs are then overlooked. They are not stored in that queue, and therefore you also cannot evaluate them, even though the fuzzer actually executed these basic blocks or functions. So in the worst case, this can actually lead to wrong or distorted fuzzer evaluations. And in the second thing is that inhibits measuring how often a code region has been executed, which is very nice to know actually in fuzzing, since there's a lot of effort spent on generating these many inputs. So having this information will allow you to identify barely tested code, or also study the impact of the amount of test inputs generated. So to address that, we developed the FASTASTIC coverage analyzer, which is based on LLVM and therefore basically works with any black box, gray box, or white box fuzzers, as long as you have the sources available. So you need to instrument your program that you want to analyze with our LLVM compiler path so that you can get the information out. And what we are doing is we are tracking basic block and function coverage, as well as the execution frequencies. I will refer to that as hit counts. And we are not only studying the inputs stored in the queue, but all of these millions of generated fuzz inputs that are generated within a fuzzing campaign. And this allows you to perform fuzz simulations that are non-distorted by these path collisions. You get these hit counts that allows you to do frequency-based coverage analysis. And you can also use this information to generate nice visualizations. So to show FASTASTIC's applicability, we generated a pretty huge benchmark data set that we will release. We also will release, obviously, the tool, so probably next week or so on GitHub. I will go back. You will find the link on the left slide there. But we also generated this benchmark data set, and you can see the 12 programs that we fuzzed in this table on the left. And we also used 9 different fuzzers, 7 from the very famous AFL family, which is a very widespread fuzzer, as well as Eclipser, which is a conconic execution engine, and HongFuzz. And we started the campaigns or each experiment with 2 different initial seeds to be also able to see what is the impact there. At first, we used an empty seed and then another corpus with non-empty seeds. We also followed the best practices recommended in the fuzzing community, that we run the fuzzers for at least 24 hours, and to account for the randomness involved in the input generation, we repeated the experiments 20 times. So what you get with that paper is a very in-depth coverage data that is worth roughly over 12 CPU years, which is quite a lot. And yeah, it is intended to be used in further studies, and it actually is already used in 2 further papers. As part of our study, we did a case study to actually analyze the path collision severity. So how bad are these path collisions really? And for this, we started, we looked at these AFL-based fuzzers, and you can see here this little picture on the right side, which is taken from Fuzzing Survey, which gives you the connections, how these different fuzzers, because there are a lot of available, are connected. And you see AFL is very widely used and is quite often used as a basis for further fuzzing tools. So this path collision problem is really widespread. And to analyze that, we used our data set that I just mentioned before. There we have over 3,300 AFL-based fuzzing campaigns. And what we then did, we measured the maximum amount of missed basic blocks when you are using this approach where you only measure coverage from the queue. And only to summarize that, it's in detail described in the paper. On 3 programs, we actually measure a deviation or a maximum deviation of 6 to 9% of missed basic blocks, which is quite a lot. So you, in a real world evaluation, you would get wrong results here, given that the top fuzzers perform pretty similarly. On 6 programs, we have a deviation of around 1 to 4%, and only in 2 programs we saw that less than 1% of the basic blocks were missed, which might be negligible. But yeah, this information is not available before, so it really makes sense to use our tool to measure code coverage. So for the rest of the talk, I will show a demo here, and I will switch for that to my editor here. Hope you can see it. So Fuzztastic is shipped with Docker files, the Docker files that we use to generate this benchmark data set. So you can look at them and see it as a template to plug in your own fuzzer or your own benchmark programs. And we also provide the script build containers here, with which you can then build a container where you can fuzz your program very conveniently. And here in this example, I will create a container for the target program lib2png, libpcap is it, which is a library for parsing and filtering and analyzing network packages. And we are using the very widespread HONGFAS graybox fuzzers. I won't create the Docker container. I already did that, so we will skip that step. So you can see here that Docker container or this Docker image is already created. But what we will do right now is we will run HONGFAS on libpcap. So for this, you can simply run that command. Let's go it step by step. So you just run docker run, and then the Docker container or Docker image that you want to have. We specify libpcap as our target program. We specify HONGFAS as fuzzer that we want to use. Here, this index value here indicates that we want to use a non-empty seed corpus. 1 would be the empty one, 2 is the not empty seed corpus. We want to fuzz it for 900 seconds, which is 15 minutes. And we want to store the results in the transfer directory. And I will just run this command, and it takes a little bit, a couple of seconds until everything is set up. But yeah, now you see that the fuzzer is doing its job. It's bombarding the target program with inputs. And what we can now do, we can look what is generated. So I will just leave the fuzzer running here, and we can take a look into the running container on this side here. So first of all, you see this directory here where you have your sources of your target program. So for example, libpcap fuzz is the instrumented program that we are currently fuzzing. Then we also have the sources of our fuzzer, which is HONGFAS here. We have the sources of our Fuzztastic tool and so forth. And now let's go to the transfer directory, which you can then also map or mount to your host directory to easily access the coverage information. So here you can see this directory was created. Then in the fuzzer directory, that's the working directory